Hi, and welcome to Build with DynamoDB. This time we're going to talk about Introduction to NoSQL Data Modeling with Amazon DynamoDB. My name is Ed Zulich. I'm a solutions architect focusing on NoSQL and specifically DynamoDB.
My name is Siva Raghupati. I lead the NoSQL non-relational solutions architecture team. Delighted to be here.
Thanks for joining us again this week. If you missed one of the sessions, either the one that was last week, which by the way was a great session with Rick Houlihan on the database office hour, which comes on right after this show, check it out. It's online, as well as our first show. Let's start off with a maybe quick refresher about some of the key concepts in DynamoDB, starting with the table and partition, sort key, table items, right? As we said last time, one of the key things when working with DynamoDB is the selection of partition key, which is mandatory. And in addition, you can have an optional sort key. We did have a question last time about what can I do with sort key? And in this session, we're actually going to get a little more into it and start talking about data modeling, right? And how to select a partition key and what we can use sort key for.
Yep.
Records in DynamoDB tables are called items, and each item has attributes. From one item to the next, the attributes can be very different. The only thing that has to be there is the partition key, and of course if you're using the sort key, it has to be there as well. So as far as
And the key has to be unique.
right, the primary key on the
Yes.
table has to be unique.
It could be just a partition key or a partition plus sort key,
Right.
depending upon whether you have a table with just the partition key or a table with a partition and a sort key. But together,
Right.
each item is identified uniquely by either just the partition key or a combination of partition
And
sort.
sort key, right. So now that we've kind of established the terminology baseline, so partition key, right? If you look at the DynamoDB APIs, basic APIs, they all use the partition key, whether we're writing an item, reading an item, or deleting an item. So it really is a foundational concept in DynamoDB. Also, if we're using batch APIs as well as query or transactional APIs, they all take partition key. You have to have a partition key. And so, for example, in case of queries, what that tells us, I can query on a given partition key.
Yep.
And so this gives you an idea what queries can do in DynamoDB. If I'm storing, let's say, sensor data, telemetry data from a number of sensors, right? I do have to query based on the partition key. So that also means that I cannot query across all the sensors.
Yeah.
And that's a key thing to know about querying in DynamoDB. However, with the sort key in the mix, I can query within the same partition key on a range of values based on the sort key.
Yeah, having a partition key kind of allows the system to partition prune, even though there may be hundreds of thousands of partitions. Dynamo fairly efficiently identifies whatever is your query pattern, since it's always contains, you always provide a partition key. It nicely goes ahead and lands in that partition and starts scanning the partition or delivering results from the partitions. It's pretty important to actually pick the right partition key, which we will go through in detail in the course of today.
And that's closely related to the latency that
Yeah.
you get
Yeah.
when using DynamoDB. With this model, you can talk about getting single-digit millisecond latency on these requests. Let's talk a little bit about denormalization and aggregates, right? If we're storing data in a relational database, let's say, for example, storing orders and order items, chances are we might have a couple of tables, right?
Yeah.
It's a very basic scenario, but we still have a normalized schema, right? And by contrast, in a NoSQL database, we would try to store related data together.
Yep.
And again, it goes back to that idea of going to one place to write or read your data. So if I'm using same partition key for my order and my order items, they will be stored close together, and I can actually use a single operation to either write or read my orders. And so while we have normalized schema on the relational side, in NoSQL databases, we denormalize data and store them as aggregates. So in this case, an order is an aggregate that I work with. I need my order data when I'm writing that order, when I'm reading an order. And so the concept of aggregates, which comes from now the book escapes me, but it's a well, anyway, it'll come back to me. I'm forgetting the domain driven design is where it comes from. But as it turns out, it really aligns well with the partitioning, sharding nature of NoSQL databases.
Yeah.
Because if we shard by partition key and we use that to store our aggregates, we always make sure that our aggregate is always together. That object, whether it's an order object, session object, shopping cart object, is stored together. And in this case, in this example, we're storing an order as a single item in DynamoDB in our case, but it may well be a collection of multiple items. The one thing that they would have in common is they would have the same partition key.
Yeah.
So our aggregates could be composed of several items, but they will always have the same partition key. So the question that often comes up is, so here we went from 2 tables to 1, and we always talk about reducing the number of tables using, whenever possible, a single table to store your data. So what are some of the guidelines that we can use to determine how many tables should we use? Right? So we just talked about one, using aggregates and those access patterns to drive that decision. Another key aspect of it that I always throw into that decision-making process is the broader context of my design and my architecture. These days, we all like to use microservice architectures, and one of the tenets of microservices is that each service owns its own data. And so in that context, if we talk about having, let's say, an e-commerce application, as in this example, and potentially many services, right? But for example, if we just focus on a subset of a shopping cart, product catalog, and account service, we should at least have one table for each service, as that allows us to keep those services separated, decoupled, basically. Yeah. If we put that now in the context of sharding and partitioning, here's an example where we're storing orders in a DynamoDB table, and partition key is the order ID, and we see that each one of these aggregates has a different order ID. If we take a look under the hood of this DynamoDB table, if we were able to do that, we would see that there are many partitions, right? And when we do a put item on any of these orders, the service will hash the partition key and figure out what partition this particular order will go to. And because they all have different partition keys, different values for the partition key, they will all end up in different partitions. And so the choice of the partition key in this case allows us to get even distribution of data across the table. And as we add more orders, as our business grows, and now instead of thousands of orders, we might be dealing with millions of orders.
Yeah.
This choice of partition key allows us to scale and just continue to seamlessly handle the growth in scale of traffic and data volume.
Yeah. In this scheme, in this modeling semantic, order ID is unique.
Right.
So we have a large number of order IDs. The larger number of partition keys you have, the better it scales. The ideal situation would be unique partition keys in this kind of schema. So I think this way, the hashing function hashes all of the partition keys into its own partitions.
Right. Your order ID is your scaling dimension.
Yeah.
And by contrast, if, let's say, in a different scenario, we decide to select a different partition key for our orders, just because you might have an access pattern that maybe calls for access by a country. And so in this example, the partition key is country code, whereas the order ID is now the sort key, the combination of two being unique. And just the country code, of course, would not be unique. So, but what happens with this data model is that because all our orders in this case, in this example, have the same country code, they all end up in the same partition.
Yeah. So this would be an anti-pattern for how to.
This would be an anti-pattern
for how to model. Maybe, and one of the ways of maybe fixing this would be, should the application concatenate the country code and the order ID and then make it unique? And then in that case, again, you have a large number of unique IDs and therefore it'll scale better.
Right.
Yeah.
And there will be cases when you do want to maybe look up your orders by country code.
Yeah.
But we'll talk about options for that, how we can
handle that.
Those cases, right?
Yeah.
So the point though is that the choice of partition key is fundamental to horizontal scaling. And in fact, as we saw in this last example, if we're not able to accomplish that, we end up with too much pressure on maybe a very small subset, or in this case, in the extreme case, too much pressure on a single partition, right? And we're not scaling. We're not scaling our traffic. We're not scaling our database, basically.
So this paradigm is applicable to all NoSQL
Exactly.
databases. It's not only a
and it's really it's really related to the sharding nature of distributed NoSQL databases.
Cool.
So the problem here, of course, is that the extremely unbalanced data or request distribution is what's preventing the ability to scale. So to kind of sum up the basic, I think, ideas behind the partition key, we're always looking for a partition key that affords even distribution of data and workload as they might grow.
Yeah.
Right? So if you're a startup and your main asset is your users and you're storing your user data, user profiles, you want your ability to store your user profiles to remain intact as you add more users. So partition key is your dimension of scale, and it allows you to distribute these aggregates, which might be user profiles or accounts, user accounts, or what have you, across partitions as your user base grows. And that's what DynamoDB is really good at.
Yep.
So ideal scaling conditions. Now, in real life, we know that we can't always have ideal scaling conditions, but it's good to know what they are, so that if we know that we cannot have all three, that we know that we might have to come up with a design to accommodate that, to compensate for the natural lack of these conditions. And in fact, as we move forward in some of these future data modeling sessions with DynamoDB, we'll talk about patterns that we use, solutions to some of these problems.
Yep.
Yeah.
So yeah, why don't we then roll into sort of the modeling relationships with DynamoDB? So we do a large number of design reviews. I think one of the primary area where we start doing the design review is trying to get a sense of what kind of answers you're trying to surface. I think we call this sort of access pattern modeling. So as part of the access pattern modeling, once you understand what kind of queries you have to service, or what kind of puts and gets you'd have to service, the next thing immediately is sort of modeling your attributes and tables for the specific scenario. There are three fundamental constructs that we will go through today. I think when you're modeling relationships, typically relationships are one-to-one, one-to-many, or many-to-many. We'll walk through in the next few slides as to how what type of constructs you can use in DynamoDB to model these scenarios. For example, if you're modeling key value relationships, using a table with the partition key as the key and the various attributes as values would be the way to model the table. In this specific scenario, let's say the first table in the middle is a user's table, and then the user ID can be a partition key, and the various attributes such as email, join dates, etc. Can be attributes. In this case, the access pattern would be given a user ID. In this case, Bob, give me all the details about Bob, Bob's email, join date, etc. And that would be the access pattern. Typically, you'd be using a get item or a batch get item API to actually get these attributes provided the keys. You could also use the query API, but typically for getting one item, get item tends to be the best use of
Most common.
usage pattern.
Performance-wise,
It's the same.
right.
The other piece is also you could potentially use a global secondary index also to actually model key value relationships. For example, if you had a primary table called a users table, you could potentially have a user's email global secondary index. In this case, the email is the partition key in the global secondary index. So if you had, let's say, another mechanism where you want to look up the users by email, so you could potentially service those lookups using the user email global secondary index. So that's what is shown at the bottom of the slide. So key values scenario is a fundamental scenario. In fact, many applications require massive scale. In a number of those applications, you are simply handling a key value, scenario, in which case modeling the scenario as a table or a global secondary index with the key with the partition key as the key is super important. So that is a large number of use cases fall into this bucket, and it's actually pretty simple and straightforward in DynamoDB. Like we talked about before, the fact that you pick a key, you don't have to deal with partitioning or repartitioning the data. DynamoDB automatically partitions the data on your behalf and spreads your data across, as number of partitions as that are needed. Each partition size is about, is 10 gigabytes. So if you put more than 10 gigabytes, it'll automatically split into multiple partitions. You don't have to deal with, partitioning and repartitioning, etc.
You really won't even know it.
You really won't even know it. The only two parameters you may have to worry about is, really choosing the partition key at one point and maybe provisioning throughput if you're manually provisioning this or auto scaling this or on demand. If you use on demand, you don't even have to worry about this. Simply a choice of a good partition key would automatically, scale the app.
Right.
So that is the first pattern. The second pattern or the data second pattern is really how do you model one-to-many relationships. In many practical scenarios, you have one-to-many relationships. In this specific example, let's assume you have a device with a device ID, and it is actually a device is supposed to measure temperatures and pressure. Let's say this device measures temperature and pressure at various time points, which is denoted as the epoch timestamp there. So if you are storing this data, you could use a table with the partition key as the device ID and the epoch as the sort key. And combination of this should be unique. That's about the only constraint you have to worry about. So once you choose that, then you can actually query this table using a query API, wherein you can say, for a given device, ID equals 1, give me all the records pertaining to this device. Or you can say something to the effect, for device ID equals 1, give me all the records or items with a timestamp greater than a specific epoch or less than or between. Semantic can also be used. So this is another powerful mechanism for modeling one-to-many relationships. Now, this device measurement, primary partition key and the sort key mechanism can be implemented in a global secondary index as well. So the same semantics apply there. So if you're using a global secondary index, then you can query the global secondary index in a similar form.
Yeah, so what's in the name? Sort key. It does mean that the data is sorted.
Actually, the data that's a great point. And the data on physically is sorted by the sort key within a specific partition. Therefore, scanning the data either forwards or backwards, becomes very easy. You can also have, use the query API and say, give me the top end records for a specific device. Give me the top end records. Like, in fact, the specification of the epoch is optional. The sort key is optional. You can simply query for all the records for a specific device, for example. Those are some of the query patterns.
Yeah, you could use equality on both the partition key as well as
the sort key as well.
Right.
Yeah.
The one nice thing about this approach, especially when it comes to sort key that's time based, is that I can always get that latest value or version for that matter, right? Yeah. I could use that sort key to store different versions of my data.
Correct. So if you are versioning the data, even if it's a key value data store, if you could use the sort key as a mechanism for versioning this, and therefore you can either get the items in the ascending order or the descending order, and then manually version this as well.
Right.
So the third semantic that often is very popular is how do you model many-to-many relationships. Here we need a base table or multiple and a GSI or multiple GSIs to model that global secondary indexes to model this relationship. In this specific example, I'm using the scenarios that of games, a user playing multiple games and each game comprising of multiple users. So there is a many-to-many relationship between users and games. So in that scenario, you could potentially use a table called user games table, where the partition key is the user ID and the sort key is the game ID. You could also have a global secondary index on the table, in which case the partition key is the game ID and the sort key can be the user ID, in which case what happens is that since when you update the table, the global secondary index gets automatically populated, you could, when you want to find out for a given user, give me all the games that the user played, you can query the primary table, the user games table. If you want to do a reverse lookup, given a game, finding out all the users, you could actually query the global secondary index for getting the data. So this comes fairly handy for scenarios where people would have to do, somebody would have to do reverse lookup.
Right. So this would be the example of inverted index, basically, where you take that sort key and that becomes the partition key on the global secondary index, and the partition key on the table becomes the sort key on the global secondary index.
And then you can implement this with two global secondary indexes as well. In fact, we'll go through one of the examples going forward where we'll actually use a base table for simply keeping the item, and then a couple of global secondary indexes to actually look at the data in two different ways. The inbox example that we will walk through. So that is it. So you have basically three constructs to model all kinds of scenarios with DynamoDB. Either you need to, if you have a key value scenario, simply use a table with a key and attributes. If you have a one-to-many relationship, use a table with the partition key and a sort key, the partition key being on the one side and the sort key being on the end side. And if you have a many-to-many relationships, then you would use a table and a global secondary index or multiple global secondary indexes where you actually reverse the keys, if you will, where your partition key becomes the sort on the other side and vice versa.
Right. And we are talking about relationships here.
Yeah.
So what's up with that, right?
Well, in real life has relationships, and you
right.
often model those relationships. And what really matters, to me, is really sort of looking at the problem from beginning with the end first. In other words, what are the query patterns? What are the answers I'm trying to surface? And then work backwards from there,
Right.
and to go design a data model using the constructs such as the partition key, sort key, and the global secondary indexes to be able to actually match that scenario's need.
Right.
Is the way to model with DynamoDB.
Yeah, and some of this really goes back to our fundamental goals that you want to accomplish at scale, and that's the ability to maintain performance at scale, which is why we talk about reducing the number of tables so that, imagine if you had an order aggregate and you use the same relational model where you have two tables and maybe dozens of orders in your order items table. You'd end up having to go to the order table and then order items table for each one of those items. Right. And of course, the larger the order gets, the more interaction with that table, the more expensive it gets, right? Whereas if you model that aggregate such that it fits in the same table under the same partition key, all that goes away, and you're using access patterns that give you what you need with a single request.
Exactly, and then the query gets materialized efficiently as well because all the other partitions are pruned, and then your data is efficiently retrieved from a specific partition that the items belong in, and then the order ID being the partition key in the scenario.
And I'm never too picky or worried about naming conventions, because at the end of the day they're just names. But that's one of the reasons why we like to say NoSQL rather than non-relational, because relationships are there, and we don't want to create an impression that you don't have relationships in the NoSQL technologies.
In fact, I think the power of DynamoDB also comes in we having the ability to model one-to-many and many-to-many relationship, and some of the NoSQL engines just have a key value semantic, and in which case it becomes very difficult to model real-life scenarios.
Right.
Cool.
Let's see what's next. Let's go with an example, and we'll start gently with an example that's fairly basic, common, and it's one of those examples that really was one of the reasons for the need for these distributed data technologies. Back in the day at Amazon, shopping cart and session services were the ones that needed to scale the most. And they really prompted the company to start looking into developing a distributed data technology. And the first incarnation of that was Dynamo. And that was now over 10 years ago. And so you can think of DynamoDB as a grandkid in a way of that sort of first version. So a real world scenario in a lot of, I think, use cases, you need a shopping cart service. And in this particular example, shopping cart turns out to be not a whole lot of data in a single shopping cart.
It's also a very critical service. If you don't have the shopping cart, then customers cannot shop, and
mission critical.
It's a mission critical scenario as well.
Right. So we're storing, as we can imagine, cart items, items that customers are buying. We're storing some additional data. We need to know cart ID. Maybe it's your account ID. Maybe it's not. But there's certainly a mapping from a user to their cart, right? And so we have an idea about the size, fairly small. We need to be able to handle millions of carts in a table. In this case, we worked with the number of the ceiling of about 100 million. So we knew the data volume itself was not very challenging, right? For DynamoDB, it's never really challenging. The access pattern was really key value. We just needed to be able to access cart data based on the cart ID.
So Eden, this is a real customer scenario
right.
that you had solved, and this is the way the requirements look like. They wanted to put 100 million carts is what they were thinking about. Even though Dynamo can handle as many millions or billions that you want to put in there.
Exactly.
There's no limits of how many carts you can put in there. But this is a real scenario that you're
right
to the customer.
Right. Exactly. And the throughput requirements were more demanding, right? The service had to handle 10,000 writes and 10,000 reads per second, right? So we are talking high concurrency in this case. And so how did we go about modeling this? Again, to kind of go back to where people usually start, right? It's a relational database, relational model, and you could imagine how in this scenario you would have a cart table and then cart item table.
Yeah.
With DynamoDB, we want to start by looking at an aggregate. In this case, the aggregate is the cart.
Yeah.
And so that means to me, if I can store my aggregates in a single table, that would be ideal.
Yeah.
Right. And so
I have a question here. In this case, potentially there's maybe two ways or more of modeling this, right? You could use a cart ID as the partition key, and an item ID
right
as the range key as well.
right or
any
sort
idea
key.
like why as a sort key as well? Used to call this the range key before.
Right.
That's where
Hash and
stuck with
range
me.
key
Well, yes,
is the
that's
same
correct,
as
yeah.
partition and
the
sort key.
So we may
Synonyms.
interchangeably use that.
Right.
I'll try to stick with the partition key and the sort key going forward, but nevertheless, same idea. So any reason why you chose to just go with the key value semantic here?
Right. We did consider both options.
Yeah.
Because it seemed convenient to have the ability to access individual items in the cart individually. Now, because they would have the same partition key, that means that they would still be co-located, stored together.
Yeah.
But that granularity seemed like a good benefit, additional benefit to have. The reason, but then it turned out, well, these carts are small.
Yeah.
Does that different data model using the item hierarchy, as we call it, where the cart items would be separate DynamoDB items, was there any benefit to doing it that way in this particular scenario? We determined that there really wasn't any benefit.
So in other words, they were okay with retrieving all the items in a cart
When they needed to.
When they needed to, they didn't have the need to retrieve, given
individual
a cart ID,
right.
a specific item ID. So if there was a need like that, we would have modeled this slightly.
And the cost of reads did not really change because the cart object itself is
fit within
fairly
the 1K.
Exactly.
Okay.
Or the read capacity unit, right, which is 4K, right? So for reads, it did not really make any difference. For writes either, right? We're still using the same amount of write capacity, and this was a simpler model.
Yeah.
Essentially,
and oftentimes
hash-based.
I realize, and if you're using a key value, the bag of bytes you can have, you could also potentially compress that even if you're having a bigger payload. So there's a lot of advantages in using a simple key value scenario if that is indeed your access pattern.
Exactly.
Cool.
And now with this model, items are stored in a collection, in a map, and you could in fact do updates where you don't necessarily have to read the entire cart. If you already have a state that cart read in your application, you can also do an update to the cart and add a new item without having to extract the whole thing or deal with the entire cart. That's still possible. One question that then of course came up was, well, NoSQL databases use eventual consistency. How can we make sure that we maintain data consistency when we update the cart? And so that's really the key concept. In fact, how do we maintain data consistency in NoSQL databases? And let's take a look at that in general. So if we're talking about adding or removing items to the cart, the algorithm essentially is this: we have to read a cart and record the current state. Usually would use a version attribute. And then when we update the cart, whether it's to add or remove items or anything, in fact, this update should succeed if the version at the time is the same version that we have. And that's how we know that nothing else has changed the state of the cart in between, right? If that fails, if that condition fails, means there has been an update and we need to reread. So we need to reread and start over, right? So
one question here. DynamoDB also has a consistent read, right? When you're reading something from a cart, you could also say consistent read equals true, and then your get will retrieve the most current value, isn't it? So in this case, what you're doing is here, you don't care to read the consistent value. You can simply not use the consistent read and simply do a regular read and
absolutely
and move on.
Even if
because writes are always consistent, so when you're writing it, if there's a conflict, you would fail.
Right, but to optimistic concurrency control is a concurrency control mechanism, right? So even if I were to use strongly consistent reads, I'd still have to use this mechanism to make sure that I maintain data consistency, right?
In this case, you're assuming multiple writers may write to the cart. So you're even guarding the scenario where you didn't read something from the cart, meanwhile somebody updated it, and you have a lost update scenario.
Sure.
So you're using the conditional update feature in Dynamo to ensure that you don't have any lost updates.
Exactly.
Cool.
And of course, as you know, an astute viewer might notice, well, what if there are a lot of concurrent updates on the same object, on the same item? And that's a fair question, right? I could be in a situation where I fail repeatedly, right? And in that case, my latency continues to grow. So write contention really is the issue here. With optimistic concurrency control, it's an approach that works really well for low write contention scenarios. The use case such as a shopping cart is actually typically one such scenario.
Especially at the shopping cart level.
Right.
So even though there might be a large number of updates to the shopping cart, like in this example, you said 10,000 writes per second.
Because the idea is that we're, in this example, we're scaling our ability to serve many users using their own shopping carts, right? And I know there might be scenarios where you might be sharing your shopping cart with your family member, for example. We're still not talking about high write contention, even in such scenarios. But we do have to have a correct algorithm mechanism to maintain that data consistency. And optimistic concurrency control is that basic mechanism to do that with distributed NoSQL databases.
Cool.
And in case of DynamoDB, right, just to show some of the JSON requests, right, what they look like. We're getting the cart. We record the version, and then on updates we can do conditional put or update item, in fact. And in fact, to go back here, this is the process, right? We do have to read the cart and get that version.
Yeah.
But we don't have to do that repeatedly.
Yeah.
Because if we're maintaining that object in memory and we do an update, let's say I'm putting more and more items into my cart, I don't have to do that read
every single time
because I'm also maintaining that object.
Yeah.
And as long as my updates go through, means that I'm actually in sync with the database, so I can continue. So back to your question, I do have to call get item, and at some point, right?
Yeah.
Should that call be strongly consistent or eventually consistent, right? Does it matter?
Yeah.
And it doesn't, because the correctness of this approach does not depend on whether I'm using
doing it consistently or not.
Because let's say that I'm using eventually consistent read. What will happen is the condition will fail.
Yeah.
And then I will just retry. I will argue that in a use case such as the shopping cart service, it actually makes sense not to use strongly consistent because typically that write contention is not going to be high.
And Dynamo consistency is very strong, Dynamo data gets consistent very fast anyway.
Exactly.
So you might as well use a regular get.
Right.
And not mention consistent read equals true.
Yeah.
And then since you're doing conditional updates, then it's totally fine. If there is a conflict, it'll fail, then you can retry.
Exactly.
Yeah.
Yeah. So I'm curious though, have we seen any questions from our friends in the chat room?
Let me check.
Yeah.
Keep going.
We have Daniel, Pete, and Sean, our teammates that are hanging out with y'all in the chat room. So to sum it up, we're using conditions in DynamoDB, condition expression to be specific, to implement optimistic concurrency control, which ensures data consistency between updates. Get item call can be eventually consistent, and you should take advantage of that. One other thing. I forgot what I wanted to say. Never mind, move on. Another example that we mentioned earlier is about using global secondary indexes to implement efficient and cost-effective.
I have one question here
Okay.
from Tulabon, and then in the case of order and order items, it is many-to-many relationships. What if we want to store one order with many items, more than 10, as one transaction? Transactional rights can only support 10 items per transactions. How would we have transactions in that case? That's a great question.
Right.
So if you're going to transact, you have a limit of 10 items, per transaction.
Right.
So I think this semantic can be used only for 10 items,
Yes.
as a whole together. And then, this is where in the modeling semantics that we have used here, many customers want to, read all of this thing as one unit anyway. So actually simply using a key and keeping all those items as a bag of bytes.
Yeah. So
can come in quite handy.
Right.
Or, kind of compressing that and spreading that across 10 items, if you will. In other words, your sort key is really a mechanism for you to get a number of items, one-to-many relationship with the parent anyway. So it doesn't have to correspond to a single item. You could potentially compress multiple items. But where this gets to be somewhat, if you're having a reverse lookup, give me an order, an item, and give me the other way around, give me the orders where this item surfaces, then literally you have to actually put that on a single item, in which case, you can transact
right.
all of them together. That would be, one of the limitations, if you will.
Right.
So,
And that does become a little bit awkward though, right?
Yeah.
Because you would naturally like to work with your business objects, right?
Yeah.
With your order items. And so another option would be to go back to using a pattern that we used to use for these scenarios before we had transactions in the first place,
Yeah.
which is locking essentially your items. So let's say you have 20 items. One of the items in that item collection in DynamoDB is a metadata item for your order, where one of the attributes is essentially a lock.
Yeah.
And so what you would do is take out the lock right to that attribute, and then essentially implement transaction yourself, make changes, do writes to those while you hold the lock, and then update the lock, right, to release it basically. So it does become just more work to do basically. But this is how we used to do it before transactions. This is how we had to do it to accomplish that basically. And that is true. The transactional API currently has that limitation, but we've actually heard more than a few voices.
Customers asking for more than 10 items. We're taking a look at that.
Right. Well aware of that request and ask. So, yeah.
But thank you for bringing that up. Great question.
Mm-hmm.
So you want to go into the second example here?
Yes. We're about 45 minutes into the show.
Yeah.
And so this example is about a messaging application where we need to show an inbox and outbox view of messages that we get. Something that's easy to relate to because it's very similar, for example, to an email client application that we all use every day. We'd like to model an inbox view where we can limit the view to, let's say, 50.
So one other question that comes up before you jump into this.
Okay.
This is question from Slot2. Love the version idea. Is there any specific reason why it is not an integer but a string? I guess Slot2 is alluding to your version identifier being a string. And not an integer. It can literally be anything that you like.
It
doesn't
really
have
could
to
be. Yes.
Because you're doing an equality check on this, on the version numbers. The version number could be an integer or a string. Great question again.
So, yeah, the only thing about that is, though, when it's an integer, we can easily basically go
an increment,
right? The version, right? That's the reason why we're going with a number.
Yeah.
So that.
Did you use a number or a string? I didn't.
I used a number.
Okay.
Yeah. So, because then it becomes easy to just bump the version, and keep going that way. So that's the reason why we would use the number there. So messaging application modeling an inbox where we need to show messages up to 50 in a single inbox view, and then same for the outbox. We're storing messages in a table. So first attempt at solving this problem, I could see essentially saying, well, we need to show messages per user, right? So why not use that recipient as the partition key, and then we do want to have messages ordered by time we receive them, so the date of the message becomes the sort key. The messages could have attachments, so we could have, in this case, a view that has up to 50 items, and each one could be up to 250 kilobytes in size. So, if we calculate the cost of such a query, 50 items, let's say that average item size is 10 kilobytes. Then we're applying the conversion ratio. We're trying to calculate the cost in read capacity units, right? So the conversion ratio uses the size of read capacity unit, which is 4 kilobytes. And then we're perfectly fine with eventually consistent reads. We still come up with 63 read capacity units every time. So let's say we're dealing with hundreds, thousands, let alone millions users, right? So every time I look at my inbox, that query would cost me 63 read capacity units.
Yeah.
And that's because my messages might have attachments, might be anywhere from a few hundred bytes to maybe a few hundred kilobytes in size.
If I attach a PowerPoint slide and
Right? 20 megabytes.
yes.
Right? So, but do I need all that in
Yeah.
my view?
Yeah.
Right? It's my inbox view.
Yeah.
I don't need the entire
Another thing that
attachment.
it does is also kind of when you're reading that many number of read capacity units from a specific partition. So, I think of this as a heat. Right?
Absolutely.
So in other words, there's a lot of read capacity units directed at the specific partition. So
Right.
I'm naturally thinking, is there a way to spread the read heat or read capacity unit
Exactly.
across multiple partitions rather than,
Right. And also intuitively, I know what's going on, right? I know that my messages could be fat, could be big,
Yeah.
and I also know that I don't need that
Cool.
in my view.
So I'm dying for the solution right now.
I know, me too. So we call it separating the bulk data, right?
Oh, cool.
Let's say we store messages partitioned by message ID in a message table. Let's see if we can use a GSI, right?
Cool.
So the nice thing about GSIs is that we can project exactly what we need in that view to the GSI.
Yeah.
And that GSI, now we do want to partition on recipient and date. And what else do we need? Sender, subject. Message ID, because it's a partition key on the table, will be automatically included, right? And interestingly enough, I have to comment on that. What is the message ID in this case? It's a foreign key,
Yeah.
basically,
Yeah.
right? From our GSI back to the table. But now my queries are a lot more cost effective. Well, they're more efficient. I'm sending less data.
Right.
They're faster
Right.
because I'm getting, instead of 500 kilobytes, I might be getting just a few kilobytes back for
Yeah.
50 messages, because each of my items in the projected GSI is maybe just not even, it's maybe 128 bytes or
Yeah,
maybe a
yeah.
couple of hundred bytes, right?
Yeah.
And the cost is down to one read capacity unit,
Yep.
right? So also the idea here is that with DynamoDB, when we have a GSI, that we satisfy our queries, we model that GSI so that whatever access pattern we need it for would be completely satisfied by querying the GSI. So when we query the GSI, we get the data that we need, and we don't need to query the table. And of course, when you click, let's say in your client app, you click on a particular item, that's when you use that message ID to access the entire item from the message table.
Cool.
And inbox GSI, same idea, right? I meant outbox, but this really shows where we select the attributes that we want to project. And now the GSI satisfies our query inbox access pattern.
Yeah.
We do the same for outbox GSI. Select the attributes, have a projection for the outbox. Partition key will be the sender in this case, maybe. That makes sense, and we're done. So our messaging app now has the main table, has a materialized view that's served by the inbox GSI, and another materialized view that's served by the outbox GSI.
Whereas the primary table is just a key, has a key, which is the message ID.
It's
and
exactly
then
just a
the
key
large-
value.
It's a key value
hash
table.
based, yeah.
Whereas the two global secondary indexes, you can think of them as views that allow you to paint your inbox and the outbox, if you will,
Right.
and then not actually read all the big messages. And then you
Exactly.
can only read those messages when somebody clicks on that
Right.
item and then wants to actually download that file or whatever is the large object is.
Exactly.
Cool.
And in fact, this really goes back to a couple of I think goals that we always have when we do data modeling in DynamoDB. Outside of trivial use cases, right? DynamoDB is about scale, and performance is scale, but cost is always a concern.
Yeah.
We want to model basically in a way that's going to be cost effective as we scale, because ultimately, it's a good problem to have,
Yeah.
but you want to solve it in a way that will continue to work as you grow.
Yeah.
And this is a really good example of that too, because we really trimmed down that materialized view. The cost of queries is not more than it really needs to be.
Yeah.
And also from the performance standpoint, we're more efficient because we're not unnecessarily querying and retrieving data that we don't need.
In many cases, actually, being cost efficient allows you to pick the right design pattern as well. So even when we design services at AWS, we design them to do their function extremely well and at low cost. So kind of in many cases, kind of optimizing on cost allows you to pick the best design pattern as well.
Right.
So costs matter, and
Absolutely.
both for cost as well as performance.
Right. I think we're just about out of time, and I was wondering if there are any other questions.
Yeah. So I think thank you for coming to this. We plan to do this session every week. So bring your questions. We intend this to be a two-way communication for us to solve these issues as we discuss these concepts as well. So if there's any more questions, please keep sending them.
Keep them for next time. Right?
Going back to the question, maybe one last one, where I think Slat2 asked, in our example, you had used V4. Even though you meant this to be a number, you put a string V4 rather than a number for version. So I think the V4 was supposed to be a placeholder for a version 4, which is a number. So which might be, we'll adjust the slides to
it's the
to
semantics.
annotate.
I think actually it's just the semantics of the of those
Of
variables.
the variables,
in the
So in fact, it is a number because
It is
it's
a number.
annotated as n.
Yeah.
But then the example shows a string. So that string, instead of V4, imagine that to be a 9 or a 10 or a number, if you will.
Exactly. Yeah.
So-
Sorry if that was confusing, but yeah. And thank you for pointing that out.
Cool. There's no more questions. Thank you for being at our session again, and look forward to seeing you again.
And we're continuing with data modeling and in DynamoDB next time.
So we're going
as
to do
well.
some advanced data modeling.
Yeah, I think so.
Cool.
And looking forward to the next
To
session
the next
with
session.
y'all.
Thank you.
Thank you. Bye-bye.
Bye.